Hello, this is Mr. Huff, and I want to go through the solution of your truss. So we started with these specifications. Sorry about the line through here. I don't know how that got in there. But here's our truss, and we assume we're going to go ahead and model this in MD solids. And if you follow your dimensions properly, this angle should be a 30.96 angle, so right here. This one is a little bit flaky. It may not behave the way you think, so let's go take a look at that. So depending on how you model your bridge in MD solids, you will end up with that angle at the far right being a 30.961 angle or a 32.275 degree angle. And it's not going to make that much difference to your calculations. In my calculations, it was shifting about 10 to 15 pounds when I had a 1,000-pound load. So it is not a big deal, this 1 degree difference. When you use MD solids, it should produce some results like this, and I'm going to suggest that once you get this screen and the screen before, that you do screenshots of those, and we'll print those out so you can put them in your notebooks. That way you don't have to copy this. It gives you a reference point to check your math along the way. The first thing we need to do is check static determinacy. So we are going to be using a pin at the left and a roller at the right. So when we run this through, looking at the number of joints, we have 5 joints in our bridge or our truss design. So 2 times 5 is going to be 10. When we look at the number of members in our bridge, we can count 7 members. And when we look at the number of reaction forces using a pin and a roller, we get 3. So 10 equals 10. So we are good to go. The first thing we need to do is solve for the reaction force at RCY. So the point C all the way on the right, we need to find that. We do this by using the sum of moments. So right here we're going to add all the moments together, and that should equal 0, which means that the moment at point B and the moment at point C have to add up to be 0. We're considering point A fixed. So we know by looking at the directions that the moment at point B is pulling down, so it is going to result in a clockwise rotation, and that would be a negative value. And we see the point, that point C, that it would be pushing up, resulting in a counterclockwise rotation, so that would be positive. We replace the moments with the formulas for moment. So that's the formula there. We plug in our numbers and we solve for RCY. And when we do that, we get a final result of 512.82 pounds. And that checks out. Once we know the reaction force at point C, we can determine the reaction force at point A. So we need to think about the forces only in this part of our solution. So we know that reaction force at A in the y direction is going to be up. Reaction force at C in the y direction is up. So we have 2 upward forces here, and then we have 1 downward force. So if we sum those all together, we end up with RAY is equal to a positive, because it's going up, 512.82, and a negative 1,000 because that load is pulling down. And when we solve for that, when we do a little bit of algebra, we get a positive pushing up for 87.18 pounds. The next thing we need to do is look at member AD. So when you look at member AD, you have the reaction force pushing up, and AD itself is pushing down. So these have to be equal and opposite. So when we sum those forces, we get that the reaction force, or the reaction force AD is equal to a negative reaction force in Y, and that gives us this value, so that we know that the member AD is under compression because that is a negative 487.18 pounds. It's got to be equal and opposite to this guy here. So that's what we see. For the next one, I chose to solve for member DB. We know AD now, and we want to solve for BD. One of the things to keep in mind is that from the perspective of point D, AD is in compression. That means at this point is pushing up. And so we have a positive push here, and that means this is going to be being pulled up too. So AD is going to be lifting up. So using a little bit of trig, using the sine function, we can solve for BD using AD in the y direction over the sine of the angle. So here is the math I did. For some reason I chose to use 31 instead of 30.961, but it doesn't make much difference to our answer. So we have the opposite side divided by sine theta, and that gives us the force in that member, and because this is pushing up on point B, that results in a positive answer here, so we're going to get a tension in this member. The next thing I chose to do was move to the opposite side and look at this member here, EC. So I want to know about EC. So we know that from the point of C, we have the reaction force C lifting up, the equal and an opposite pushing down. So from the point of view of EC, we have a force that's going to go this way. So we're solving for the hypotenuse. We know this opposite side, it's equal to AC and Y, which is equal to negative 512.82 that we got from solving RCY. So we have the negative value of ECY divided by sine theta, and sine theta I'm using in my model is 32.275. So I get that EC is a negative value of 960.36 pounds. And because it's negative right here, pushing down this way, that's going to be in compression. Alright, so now let's take a look at BC going this way, probably. So this line here. Okay. From the perspective of point C, EC is pushing down this way because this member is in compression. And that means when we look at BC, it has to be equal and opposite to EC in the x direction. So we end up with this inequality, negative BC is equal to EC in the x direction. Okay, so when we start from there, then we can look at EC in the x direction is equal to, is a cosine function, so we take the hypotenuse times cosine theta. So we can say that negative BC is equal to EC cosine theta. And when we plug in some numbers here, we have negative BC equals a negative 960.36 times cosine of 32.275. And we end up with two negative values. We can cancel that out. So BC is equal to 811.97. And that means this is in tension. So C is being pulled this way as the compression here pushes it this way. The next member I want to look at is EB. So if we look at this from the perspective of point E, we have compression pushing this way. That's not what I wanted to do. We have compression pushing this way, and that means we have an ECY force here. EB has to be equal and opposite to ECY. So ECY is going to be equal to negative EB because EB is going down. And we look at the sine function here because we know this angle and we're looking for this sine. So sine is opposite over hypotenuse, so ECY divided by EC. So we know that ECY is equal to EC sine theta. So EC sine theta has to be equal to negative EB. And then we plug in our numbers. EC sine, because this is in compression, our value for EC is negative 960.36, and our angle is 32.275, and that's going to be equal to a negative EB. And when we calculate this out, we end up with two negatives, and we cancel those, and we hit 512.81 pounds. I left out pounds, sorry, but that's for EB. So that means EB is in tension. So if you're looking at point E, this is being pulled down from E to B. Alright, next let's take a look at member DE. What's happening here? If we look at from the perspective of D, we have a tension pulling this way, and that means the horizontal component of DB has to be pulling to the right, and that means the reacting force of DE has to go to the left. So dBx is equal and opposite to DE, so we're giving DE a negative sign. And to solve this, we're going to use a cosine function. We know this angle here is 31 degrees, or 30.961. So cosine of the angle is the adjacent divided by the hypotenuse, dBx over dB. Alright, so dB cosine theta is equal to negative dE. In this case, dB is under tension, so it's positive. So we take that and multiply that times cosine of 30.961. We get a negative value of dE. So that means that 811.99 is equal to negative dE. We flip the signs over to make this positive, so dE has to be negative 811.99 pounds, and that means this side is in compression. That brings us to our last member, AB. And this one I'm actually going back and looking at summing the forces. So we know that right here, the sum of the forces on AB have to be equal 0 because this is a static truss. And that means that you have BC pulling to the right from the perspective of point B. And you have the X component of dBx pulling to the left and AB pulling to the left. So the sum of these two have to be equal and opposite to this. So we write this down like this. BC minus dBx minus AB has to equal 0. And then we rearrange that to solve for AB. And that means approximately 811 pounds minus 811 pounds. That equals 0. I think in my math I was off about 0.02. But that's a rounding thing. But you end up with 0. So AB has no tension in it. There's nothing going on here. So you end up with, because those two cancel out. Let's go look at that bridge really. What that means is that member AB could be removed. What that means is that member AB could be removed if the load at point B is static. So if you don't have any movement across your truss, you don't need AB. If you have movement going across the truss, though, you would need it to prevent it from shearing. Back and looking at our bridge analysis in MD solids, we see that this member is in compression, and this is the horizontal direction, and this member is in tension. So these two numbers are equal and opposite. So if you just look at the horizontal components here, you can see that these two would cancel each other out, and that's why this one is 0. Alright, I hope that's enough to get you through the calculations of your own trusses so that you can go with your load here and identify everything that's going on.